Hello and welcome back. In today's video we will introduce phototransistors, also known as infrared receivers. Who would have guessed that infrared receiver is just another type of NPN transistor? If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. Today, we will take a closer look at the QSD123 and QSD124 plastic silicon infrared phototransistors. On screen, from left to right, we have manufacturer's rendering, real-life photo and symbol used to depict phototransistors in electrical circuits. These devices are phototransistors designed to detect infrared light. They are enclosed in an infrared transparent black T1/3/4 package, which helps filter out visible light and improves performance in daylight conditions. The QSD123 and QSD124 use a silicon PNPN phototransistor structure, providing high sensitivity to infrared radiation. This makes them suitable for a wide range of sensing and detection applications. They are optically matched with infrared emitters such as the QED12X, QED22X, and QED23X series. This matching ensures efficient optical coupling and reliable operation. Another important feature is the narrow reception angle of about 24 degrees. This allows the phototransistor to respond mainly to light coming from a specific direction, reducing interference from surrounding sources. The package itself is made of black epoxy, which acts as a daylight filter and improves the signal-to-noise ratio in typical lighting environments. Overall, these devices offer high sensitivity, directional response, and reliable infrared detection, all in a compact, lead-free environmentally friendly package. First, we need to dispatch with ambiguity as how this component can be a NPN transistor. It only has two terminals, collector and emitter, whereas common NPN transistor has three, collector, emitter and base. So, where is the base on phototransistor? How do we bias phototransistor without base terminal? As the name suggests, phototransistor is managed by light, or in our case, by infrared light. So, the receiver, the plastic housing itself, is the entire base terminal. In this case, base current is generated by the infrared light. No infrared light, no base current, the phototransistor is in cutoff mode. But, when we irradiate phototransistor with infrared light, from infrared LED for example, the photovoltaic effect in receiver will generate a small amount of base current and drive the phototransistor in active mode of work. Simple enough. The mystery of base terminal in phototransistors is solved. If you haven't seen the previous video, I recommend watching it first, because we covered the datasheet and all the key concepts in detail there. In this video, for the sake of brevity, we'll only go over the main points and focus on the practical aspects. The absolute maximum rating section of the datasheet tells us maximum values, obtained under very specific test circumstances, that component can endure, without damage. The first two parameters are pretty self-explanatory. They refer to minimum and maximum operating and storage temperatures, under which the component performs, or can be stored, without permanent damage or degradation in performance. The next two parameters specify the allowable soldering temperatures for manual soldering with a soldering iron and for automated soldering using machines or robotic systems. The first parameter indicates that the component can withstand exposure to a soldering iron at 240 degrees Celsius for up to 5 seconds without sustaining damage. In practical terms, this means that when the soldering iron is set to 240 degrees Celsius, the soldering operation must be completed within those 5 seconds time limit. The second parameter defines the maximum temperature and duration the component can tolerate during automated soldering processes. For both soldering methods, the following recommendations apply. RMA flux is recommended, methanol or isopropyl alcohol may be used for cleaning, and the soldering iron tip should be kept at least 1.6 mm away from the plastic housing of the phototransistor to prevent thermal damage. Next parameter tells us that maximum DC voltage that we can use as power source to power our phototransistor cannot exceed 30 volts. Simple enough. If we were to flip the phototransistor and connect emitter to positive and collector to negative terminal of the power source, this parameter tells us that 5 volts is the maximum value of the power source that our phototransistor can survive without damage when inserted the wrong way in electric circuit. Let's remind ourselves that power is calculated as the product of the voltage drop across a component and the current flowing through it. For this phototransistor, the maximum power it can safely dissipate is 100 milliwatts at an ambient temperature of 25 degrees Celsius. For continuous DC operation, it is recommended to use roughly half of this value to avoid overheating. Additionally, the power dissipation decreases linearly by 1.33 milliwatts for every 1 degree Celsius increase in ambient temperature, when ambient temperature is above 25 degrees Celsius. Next are electrical characteristics for our photoresistor. Same as before, values in these characteristics are obtained under very special test conditions, and more likely than not, are not applicable in real-life scenarios. So, let's get on with it. The first item on the list is peak sensitivity wavelength. This parameter tells us that photoresistor is attuned to be most efficient when base is irradiated with infrared light of 880 nanometers wavelength. This doesn't mean that we cannot use infrared LEDs with different peak wavelength, just that the photoresistor most actively responds to 880 nanometers wavelength infrared light. In phototransistors, the reception angle defines the angular range or field of view, within which the device can effectively detect incoming light. It describes a cone-shaped area around the device's optical axis where light irradiation causes a significant change in the collector current. In a phototransistor, the collector-emitter dark current is the small leakage current that flows through the device when it is in complete darkness and a voltage of 10 volts is applied across the collector and emitter terminals. The maximum value for this current is 100 nanoamperes. This parameter varies with different values for VCE voltage. Collector-emitter breakdown in phototransistors is the maximum voltage allowable between the collector and emitter before the device suffers from rapid, often destructive, current increase, usually occurring with an open base. This parameter tells us that if we use anything above 30 volts for collector-emitter power source, and do not limit collector current below 1 milliampere, the phototransistor will fail. Emitter-collector breakdown parameter tells us that if we accidentally flip phototransistor in the circuit, apply 5 volts of collector-emitter voltage across terminals, with an open base, which for phototransistors mean in the dark, and do not limit emitter current below 100 microamperes with resistor, the phototransistor will fail. Now, this is where it all comes together. This parameter tells us what is needed to put phototransistor in active mode of work. So, let's see. The note number 5 says that this parameter is obtained when using infrared LED with wavelength of 880 nanometers. The voltage applied across collector-emitter junction is 5 volts, and phototransistor is irradiated with infrared light of 0.5 milliwatts per cubic centimeter power. When these parameters are met, the phototransistor goes into active mode of work, and collector current is in range between 4 and 16 milliamperes for QSD123, or between 6 and 29 milliamperes for QSD124 phototransistor, respectively. Please note that a light intensity of 0.5 milliwatts per cubic centimeter power is considered a low-level to moderate-level intensity. It represents a gentle, therapeutic level of light power, far below the threshold of immediate safety concerns. Saturation voltage in a phototransistor is the maximum voltage drop across the collector and emitter junction when the device is fully turned on by light, acting as a closed switch. Maximum value is 0.4 volts, when collector current is limited to 0.5 milliamperes. This low voltage represents the maximum collector-emitter voltage at high light levels, often influenced by temperature and collector current. Please note that test condition number 5 applies to this parameter as well. Last two parameters tell us how much time it takes for phototransistor to switch from cutoff to active mode of work and vice versa. Under test conditions of 5 volts for collector-emitter junction, resistive load of 100 ohms, and collector current of 0.2 milliamperes, it takes 7 microseconds for the transistor to change its mode of work. Pretty fast. At the end, we also need to show how to identify collector and emitter terminal on phototransistor. It is identical to all other types of LEDs. One connector is longer than other. The longer connector represents collector, which goes to positive terminal of power source, and shorter connector, the emitter goes to negative terminal of the power source. Also, if you pay close attention to the body of the phototransistor, you will notice that there is a notch, where circular body of the phototransistor has been flattened. That notch indicates emitter connector. Well, this was a lot of fun. We have learned everything there is to know about phototransistors. In next video, we will implement all we know about infrared LEDs and phototransistors, and design and implement detection circuit based on infrared light, so stay tuned. Before you leave, please give this video a like, post a comment, and subscribe to the channel. Thank you and bye.